Hello friends, very good morning. Myself Dr. M.H. Annaya, and in today's session we are going to learn a very important problem on the design of a shaft. So here the question for today's session reads like this. A commercial steel shaft is required to transmit a torque of 450 Newton meter and a bending moment of 3300 Newton meter. Friends, this is a clear indication that the shaft is subjected to combined bending and torsion, and is asking us to find out, determine the A part, the diameter of the solid shaft required. So to transmit this amount of torque and bending moment, he is asking us to find out what should be the diameter of the solid shaft. Friend, if you just refer to the data handbook, we have an equation and we have worked out such problems in the previous sessions also, where the shaft is subjected to combined bending and torsion. For such a case, we have the shaft diameter given by the formula D is equal to 16 over pi into tau Vd kTmt square plus kbmb square. This is raised to the power half. The whole thing, including this, raised to the power of 1 by 3, is the expression that is used to find out the diameter of the solid shaft. Friends, here D is the diameter of the solid shaft which is required to be found out. We know the value of this MT, MB, then tau Vd, etc. So let us write down these parameters one by one. Friends, here, first of all, this D is to be found out. So it is put under a question mark, and we have this MT is equal to 450 Newton meter. So 450 into 10 to the power of 3 Newton millimeter. Similarly, we have got this MB, the bending moment. MB is the bending moment, that is equal to 300 Newton meter. So 300 into 10 to the power of 3 Newton millimeter. We have this tau Vd. What is tau Vd? See in the question, he has not given the value, but he says it is a commercial steel shaft. So friends, for this, the value will not be given. As engineers, we should know what is the value of this shear stress, a permissible value. So here, as per the ASME code, that is American Society of Mechanical Engineers code, he says if it is a solid shaft, the value of this tau ED, or the allowable shear stress for the commercial steel shaft, is 40 Newton per millimeter square, or 40 MPa. So this is very important, and all the students and teachers should remember this value. So this is as per ASME code. As per ASME code, the value of tau Vd is 40 Newton per millimeter square for a commercial steel shaft. Friends, we are left with this Kp and Kt. So friends, Kb is equal to 1.5 and Kt is equal to 1, assuming that the loads are steady. So friends, we know each and every term on the right hand side of this expression. We will substitute these values and get what is the diameter of the solid shaft required. So friends, here let me put these values one by one. So this is equal to 16 over pi into tau Vd is 40. Then we have this Kt 1, Mt is equal to 450 into 10 to the power of 3. Kt is over Kt whole square plus Kb is 1.5 into 300 into 10 to the power 3 is the value of MB, that to the power 2. This quantity to the power half, and the whole quantity on the right hand side is to be raised to the power 1 by 3. Friends, you know all the parameters on the right hand side of this expression for D, get the value of D. And if you calculate, friends, this D works out to 43.27 mm, 43.27 millimeter. This is the answer for the first part of the question. Friends, this answer I'm not going to round it up because we are going to have later on the comparison of this hollow shaft and the solid shaft after completing the second part of the question. Friends, now after completing the first part of the question, let's see what is there in the second part of this question. Friends, here is asking us to find out for the same information, for the same data of the torque and the bending moment. He is asking us to find out the dimensions of the hollow shaft. When we say dimensions of the hollow shaft, it is the outside dia d0 and the inside diameter di. Friends, already we have done few problems using this equation for the hollow shaft. Here, friends, the expressions for the value of D for both D and D0 are almost similar, except in the place of this capital D, we will have D0, the diameter of the hollow shaft, and again in the denominator, we have got 16 over pi into tau Vd multiplied by 1 minus k to the power of 4. This is the only difference between the value of D0 and capital D. Friends, you know all the values of KT, KB, MB, MT, tau Vd, and the value of K is the ratio of Di by D0, the ratio of inside diameter to outside dia, and it says Di is 0.8 times D0 or Di by D0 is equal to 0.8. So with this substitution here, friends, all other values remain the same, and if you substitute this value and simplify, friends, you get D0 is equal to 51.58 mm. So this also I am not going to round it up. We will keep it as it is. So this is the answer for the second part. That is the outside diameter of the hollow shaft is so much. Then what is the inside diameter? The inside diameter is 0.8 times the outside diameter D0. So which is equal to 0.8 times D0 is 51.58. 51.58. Friends, this works out to 41.27. That is 41.27 is the inside diameter of the hollow shaft. So we have got D0 and Di. These represent the dimensions of the hollow shaft. Friends, we have completed two parts of this question. Then next comes the third part. The third part is what is the percentage saving in the weight of the material. So in place of solid shaft, if you are making use of a hollow shaft, what will be the saving in the material or the percentage saving achieved using a hollow shaft? Friends, for this part, let us say we will take a unit length. It could be a meter, a centimeter, whatever it may be. We will take unit length of a solid shaft having that diameter. Similarly, same length, unit length of a hollow shaft with the dimensions we have arrived at. And we will find out based on the area cross section and the density of the material. Here you should remember the densities of the materials are the same when you are making a comparison, and the lengths are also same. So let us find out what is the ratio of the weight of the hollow shaft to that of the solid shaft for unit length. So I will write down here for the part C, we will write down what is WH divided by WS. WH is the weight of the hollow shaft. So how do you obtain that? Friends, we know for this hollow shaft, the area of cross section is pi by 4 d naught square minus di square. It is the area of cross section multiplied by the length will give you the volume of the material multiplied by rho, the density of the material, will give you what is the weight of this on the same lines. Friends, for the solid shaft, you have got diameter d and the area of cross section is pi by 4 d square. Length remains the same for both. Density is also same. So if you are able to arrive at this value of WH by WS, friends, you can see here the length gets cancelled, the density of the material is the same, gets cancelled. This pi by 4 is a common term. So we are left with the equation d naught square minus di square divided by d square. Friends, we know the value of the outside diameter of the hollow shaft, the inside diameter, and the diameter of the solid shaft. So we have the values, make the substitution, and if you make the substitution and simplify, friends, you will get it as 0.5113. 5113. That is to say, the weight of the hollow shaft WH is 0.5113 times weight of the solid shaft. That is to say, the weight of the hollow shaft required is slightly more than 50% of the weight of the solid shaft. Or we can say the percentage saving, in weight of material using hollow shaft is given by 1 minus that ratio, which is 0.5113 multiplied by 100 to get the percentage. So this works out to a saving of 48.87. So what is the meaning of this? It says to transmit this power and torque and the bending moment, the weight of the material that is saved by using a hollow shaft is around 48.87 compared to that of the solid shaft. So this is the saving achieved by using a hollow shaft in place of a solid shaft. Friends, we have completed 3 parts in this question, and finally is asking us to find out what are the angular deflection, that is the deflection the shaft undergoes while transmitting this torque and bending moment. Friends, we have already used such equations before in some of the videos. Here we have to find out what is theta s, that is angle of deflection of the solid shaft, and theta h, the angle of deflection of the hollow shaft. Friends, for the solid shaft, friends, you have got the equation of this expression given by the solid D is equal to 584 mt into L divided by g theta s to the power of 1 by 4. So the solid diameter is 584 mtl to the power of 4 by this g theta s. Friends, here we know the value of this d. Mt is known to us. Length we can take it as 1 meter or 1000 mm. The value of g remains the same. So you can take it as 80 into 10 to the power of 3 per steel, and then you will be able to find out what is theta s. So in this expression, we know d, theta s can be found out because we know mtl and g. And friends, this value of the angular deflection of the solid shaft works out to, that is theta s, is the angular deflection of solid shaft works out to 0.937 degree. Similarly, friend, you have the separate equation for the angular deflection of the hollow shaft, and that is obtained from the equation d naught is equal to 584 mt into L divided by g theta hollow theta h multiplied by 1 minus k to the power of 4 whole raised to the power of 1 by 4. Friends, here we know the outside diameter. We have calculated in the first step. G, you can take the same value, that is 80 into 10 to the power of 3 Newton per mm square. K value is known to us, that is 0.8. This L is 1000, mt is given to us. If you simplify this, you get d naught, or you can say theta h in this question is equal to 0.7861. 0.7861. Friends, you are able to solve the complete problem. And friends, if you observe here in the last bit, that is the fourth part of the question, the angular deflection of the solid shaft is 0.937 degree, whereas for the hollow shaft it is just 0.7861. So you may remember or recall that while studying strength of materials, you have proved that a hollow shaft is stronger and stiffer than a solid shaft for the same torque, same value of torque to be transmitted. So you can say that the answer you have got is right. That is, in all such cases, whenever a solid shaft and a hollow shaft want to transmit same amount of torque or just bending or combined bending and torsion, it is proved that a hollow shaft is stronger and stiffer than a solid shaft. Thank you, friends.